All right. So I hope that it is audible to everyone. Yes. Okay. So let's take up the topic that is torque. And what is torque? As the name suggests, as it suggests, but still torque would mean uh, a rotational analog of force. And it's a rotational analog of force. And so therefore, what do we mean by force then? What does a force do? When we say that uh, the force is nothing is nothing but an agent which changes the acceleration of the system. Okay? It causes acceleration. Okay? And what will a torque do then? The torque over here would cause a change in what? A change in the omega of the system. Fine. A change in the omega of the system. That's what a torque would do. Here we'll write one condition that if what is constant, if the mass is nothing but a constant, and over here we'll write that if what is a constant, if the moment of inertia is a constant. Why is that? That's how we define a force, right? Rate at which the linear momentum of a system changes. So if mass is constant, then only it will cause an acceleration. Otherwise, it changes the linear momentum. In the same way, the torque over here, just as the force causes a change in the linear momentum of the system, in the same way, the torque over here, it causes a change in a quantity called as angular momentum. Okay? And therefore, over here, it is nothing but the rate at which the system's L change. Now, what is angular momentum? We will come to that in the later videos. But for now, think of it as an rotational analog of force. Fine. Okay. So, for example, this is one way in which we define the quantity called as torque, right? And what is the other way? The other way is that over here we'll define also that torque is nothing but given as cross product between the position vector and the force vector and r cross f it is. And now what is r and what is f? Take over here a door. That's the classic example. Even in the classroom, you can say that. So nothing but a door over here. Right? And this would be the axis of rotation. Right? Right? The hinges. And over here, there is one handle, right? So what do you do to open this door? You apply a force over here this way, right? Fine. What if you apply this force very, very close to the axis? Very close to the axis. Do you think that you'll have difficulty in opening the door? Yes. As you go far and far away, it becomes easier to open the door with the same amount of force. Fine. So what matters to open the door is not the force, not the force only. It's also the distance from the axis. So therefore, over here, to change the rotational state of this door from rest to that of motion, you need to apply this quantity called as torque. Similar to how you need to apply a force to change the translational state of a system. Right? Okay. So now what we do over here, this distance from the axis is nothing but the r vector, the position vector. Right? And the angle between the r vector and the f vector is nothing but the angle, which is, in this case, it would be 90 degrees. Generally, how you apply the force, you apply it perpendicular to the door, right? So, but if there can be cases where it is non-90 also, fine. And this torque is a vector. So what is the direction of this vector? Which way the torque vector will point? It's along the direction of r cross f. Now you will know how to do the right hand thumb rule, right? You can say the right hand screw rule, you can do the right hand thumb rule. You have to construct a plane made up of the r vector and the f vector. And if you go from the r cross f this way, you notice that the thumb is pointing which way? Downwards. Fine. So this represents the direction of r cross. Fine. Fine. And therefore the torque is pointing in the downward direction because the door is opening this way. So the torque will be downwards. Fine. This part is clear. Now, what is the magnitude of this torque? We'll argue that it's the magnitude of r cross f vector, which is rf into sine of the angle between r and f. Fine. Fine. So over here, let us also take it to the next step. This is one way of writing the torque, right? What is the other way of writing this torque? Okay. And over here, let us consider that this is nothing but a frame. The x-axis, this is the y-axis, and this is an object over here, any rigid body. And over here, you apply this quantity called as force, and F vector. You're trying to measure the torque of the force about which point? About the origin. Fine. Torque of F about the origin. So the measurement of torque is the origin. You draw a r vector from the origin to the point F. And this way. This is which vector this one is? This is the r vector. Fine. So therefore, now let's do one thing over here. Let us just extend the line of action of the force backward and forward in both directions this way. Fine. And let's just draw over here the angle between R and F. This is the angle, right? Conversely, this would be the angle. And let's draw a perpendicular from this point to the line of action. This one is also known as line of what? The line of action of the force. Now you notice there is a right triangle formed, right? There are actually one right triangle, not two. The hypotenuse is nothing but whom? Hypotenuse is this particular r over here. Right? So what is r sine of theta? Can we argue that this is nothing but the r sine of theta? Can we also argue that it's a perpendicular distance from the origin to the line of action of the force? So you write it as r perpendicular. Fine. Fine. So now what is the magnitude of the torque? Is nothing but r sine theta times f, which is nothing but r perpendicular times of f. Fine. This part is extremely clear. Effortless it is. Right? Okay. So now This is one way. In the same way, if you were to extend the line, if you were to split the force into its two components, uh, that is F cos of theta and F sine of theta, and you were to write over here the force F into its two components, we can also write the torque as equal to R multiplied by the force which is perpendicular to the direction of R. This way also we can write. Fine. Why? What is F sine theta? F sine theta is nothing but the component of the force which is perpendicular to whom? Perpendicular to the R at 90 degrees to the R. Fine. So both ways it's perfectly valid. Fine. And what about the sense of this torque? Since it's a vector, right? Notice how about the origin the force is in this particular sense. You just try to rotate it around it, and using the right hand thumb rule, it will point in the inward direction, the negative z-axis direction, not the outward, inward. So, okay, so sense is important over here. So let's take a short example on this first. Fine, short example we'll take because they are important. Fine, example. What example shall we take? Let us say that there is an object over here, and this is the hinge over here. Fine. This distance is nothing but 3 meters. There is a force acting this way. This is 37 degrees. And this force over here, it has 10 newtons of magnitude. Fine. This is, let's say, the origin. And there's another force over here, which has a magnitude of 20 newtons. And this distance over here is, let us say, 6 meters. And this angle is 90-degree angle. We are asked to find out the torque net and the sense of the torque. Fine. Sense of the torque. About which point? About the point O. Fine. Fine. So how do we ah fine. Just give me a minute. Something else. Let me just pause the recording.